Hey everybody, welcome back to another college algebra video. This is section 3.2. We're going to be talking about synthetic division. I'm going to show you how to use the remainder theorem to evaluate a function, and I'm going to show you how to test potential zeros of polynomial functions. Here we go. First, let me introduce you to the synthetic division process, and I want to help you understand why we use synthetic division instead of long division. Synthetic, means fake. So what we're going to do doesn't feel or look like division, but it does accomplish the same thing as long division, as long as we're dividing by a binomial in the form x minus k. That is, our x cannot have a coefficient other than 1, and it can't have a power other than 1. We can't have a binomial that starts with 3x squared, for example. It only can start with 1x to the first power. Now, just for comparison, I'm going to take you through the long division process, and just keep in mind we won't have to do this, so I'm not going to go through it very slowly, but I want you to just see what the synthetic division process is helping us to avoid. So here we go. X will go into 3x to the third, 3x squared times, and now multiply back and change signs and add. Pull down your next term. Now x will go into 10x squared 10x times, multiply back, change signs, and add. And now x will go into 40x 40 times, now multiply back, change signs, and add. And because there's nothing left to pull down, this 10 is a remainder. And you remember from elementary school, when you have a remainder, it becomes the top of a fraction, and the bottom is what you were dividing by. So we'll have here plus 10 over x minus 4. So our quotient is 3x squared plus 10x plus 40 plus 10 over x minus 4. Now let me show you the synthetic division process, and I'm going to go through it with you in more detail on another slide, but here just let's get it for comparison purposes. So what you do is, instead of copying the whole polynomial, you just copy the coefficients. And instead of copying the divisor, you just copy what would make this binomial equal 0. Well, this binomial would be 0 if x were 4. So I'll put a 4 here, and I put it in a little box to separate it from the coefficients. Alright, now I pull down the first coefficient. I multiply 4 times 3, put the answer here. Now add. Now multiply 4 times 10, put the answer here. Now add. Now multiply 4 times 40, put the answer here. Now add. Now these are the coefficients of our quotient, but you just have to know that the x power on this coefficient is 1 less than the x power of the polynomial we divided into. This was 3x to the third, therefore this will be 3x squared. So our quotient is 3x squared plus 10x plus 40 plus 10 over what we were dividing by, which was x minus 4. So you see how we got the same quotient as we did the other way, but with a lot less work and with a lot less space used on our paper. So that's definitely a win-win. Now let me give you just a little word of caution. To avoid errors, use 0 as the coefficient for any missing terms, including a missing constant when you set up your problem. For example, if you needed to divide into this polynomial, 5x to the fourth minus 6x squared plus 4, notice that the exponents jump from 4 to 2. The x to the third term is missing, and it jumps then from x squared term to constant term, so there's an x term missing. But when you set up your coefficients, you need to have every power of x represented from the largest one down to the constant. So when I copy my coefficients, I would start with 5 because that's the coefficient of the largest power, but then the next power, the x to the third, is missing, so I'd put a 0, and then I'd have the negative 6, and then the x term is missing, so I'd put a 0, and then I have the 4. You just need to make sure that you use zeros as placeholders for any x powers that are missing from your polynomial. Now here's example 1. It says use synthetic division to divide 5x to the third minus 6x squared minus 28x minus 2 by x plus 2. So let's copy our coefficients, and we notice that this starts with x to the third, and then x squared, then x, then constant, so there are no missing terms. We won't need any zeros on this one. Let's copy the coefficients: 5, negative 6, negative 28, negative 2. Then in the box, we'll put what makes this expression equal 0. So if x were negative 2, this would be 0. Put negative 2 in the box. And now let's go through our process. We leave a row blank because we're going to need to write numbers in that row. So pull down the 5. Now multiply. Negative 2 times 5, put that answer here. Now add. Negative 6 plus negative 10 is negative 16. Put that answer here. Now multiply. Negative 2 times negative 16 is positive 32. Put that answer here. Now add. Negative 28 plus 32. Put that answer here. Now multiply. Negative 2 times 4 is negative 8. Put that answer here. Now add. Negative 2 plus negative 8 is negative 10. And that will be our remainder. So the quotient we get, remember, is going to start with one less power than the polynomial we divided into. That was 5x to the third. So this will be 5x squared minus 16x plus 4. And then this is our remainder, so we'll have minus 10 over x plus 2. Now here I've written out all the steps for the synthetic division process, and it really looks more complicated when you write it down than it actually is. You've been through the process a couple of times now, and you can see that it's not a difficult process, but I did want you to have the steps. So let's take just a problem like this one and go through it while we look at the steps. So first, write all the coefficients of your polynomial in descending order of the variable. If any powers of x are missing, put a 0 where that coefficient should go. So let's see, I'm starting here with x to the third, and then x to the second, and then x to the first, and then the constant. So there are no missing powers. We won't need a 0. Let's go ahead and write down our coefficients. And then leave a space for a row of numbers and draw a line. And place a box like this to the left of your coefficients. And write k in the box. Now k, remember, is what makes this equal 0. So that would be negative 3. And now it says pull down the first coefficient. So pull down the 6. Multiply by the number in the box and write the answer under the next coefficient. So negative 3 times 6 is negative 18. That will go here. And now add that number to the number above. 10 plus negative 18 is negative 8. Now continue that process until you run out of numbers. So negative 3 times negative 8 is 24. Negative 16 plus 24 is positive 8. Then negative 3 times 8 is negative 24. And negative 8 plus negative 24 is negative 32. So these are the coefficients of our quotient, and negative 32 is our remainder. We have 6x squared minus 8x plus 8 minus 32 over x plus 3. Now it's important to realize that any statement we can write in a division form, we can also turn around and write in a multiplication form. You probably learned this when you first learned how to do long division back in school. If you wanted to divide, say, 348 divided by 7, you could do the long division process. And then to check, you could take your quotient and multiply it by your divisor, and then add your remainder to that, and it should add back up to the number you divided into. So let's see. Our dividend should equal our quotient times our divisor plus our remainder, and it does. 49 times 7 is 343, plus 5 gives us 348, so it works. Let's try that same process on the polynomials we divided in example 1. We've already done this. Here is the synthetic division, and let's now try to write it in a multiplication form. Okay, so we should be able to write that this polynomial that we divided into is equal to our quotient times our divisor plus our remainder. There's our dividend. We should be able to write that as quotient times divisor plus remainder. And our remainder just happened to be negative, so I wrote it as minus 10. Okay, let's generalize that a little bit. This is what we just saw. We can take any polynomial and divide it by this first degree binomial, and we're always going to get a quotient and a remainder. Our remainder might happen to be 0, but we always end up with quotient and remainder. Now we just saw that that can be rewritten this way. A polynomial can be written as the quotient times the divisor plus the remainder. Now, if you wanted to evaluate this polynomial at a number like, say, call it k, then p of k would be equal to q of k times k minus k plus r. So here it is written with the k's in there. You can see when we plug in the k's that k minus k is going to make 0. So this whole thing is going to add up to 0, and all you're left with is that p of k equals r. So p of k equals the remainder of p of x divided by x minus k. And we have just developed the remainder theorem. The remainder theorem says that any polynomial f of x can be evaluated at k if we work out f of x divided by x minus k. The remainder of that problem will be f of k. So let me give you an example. We've already worked this problem back in example 1, and we looked at it again after that, and we found out that this polynomial divided by x plus 2 equals 5x squared minus 16x plus 4, remainder of negative 10. Well, now let's notice that this is f of x divided by x minus negative 2. So if we think about it like this, where we're dividing by x minus k, our k would have to be negative 2. Let's evaluate f of negative 2 and see what happens. I'm betting that we'll find a function value equal to our remainder, but let's see. So plugging negative 2 in here, we'll have 5 times negative 2 cubed minus 6 times negative 2 squared minus 28 times negative 2 minus 2. Now negative 2 to the third is negative 8, and negative 2 squared is positive 4, and negative 2 times negative 28 is positive 56, and then we have our minus 2. This is going to make negative 40 minus 24 plus 56 minus 2. All of that adds up to negative 10. Okay, so f of negative 2 can be evaluated by plugging in the negative 2, and it can also be evaluated by doing the synthetic division with negative 2 in the box and finding the remainder. Either way we want to do it. Now for some functions it might be easier to plug in the number directly, but for other functions like this one, it might be easier to just do the synthetic division with the number where you want to evaluate showing in your box. Let's see this on example 2. This says let f of x equal negative x to the fourth plus 3x squared minus 4x minus 5. Use the remainder theorem to find f of negative 3. Okay, we know we could find f of negative 3 by plugging in negative 3 here, but that wouldn't be using the remainder theorem. The remainder theorem says that f of negative 3 will be the remainder of our function divided by x minus negative 3, which actually ends up looking like x plus 3. Okay, so let's try it out. Notice here we start with x to the fourth, and we don't have an x to the third. Remember, when we put our coefficients down, we'll have to put a 0 to hold the place of the missing x to the third. Okay, our coefficients are going to be negative 1, 0, 3, negative 4, and negative 5. We want to evaluate f of negative 3, so let's put negative 3 in the box. Now pull down, multiply negative 3 times negative 1, now add. Multiply negative 3 times 3, now add. Multiply negative 3 times negative 6, now add. multiply negative 3 times 14, now add, and we find out that the remainder is negative 47. So that's telling us that f of negative 3 is equal to negative 47. Now, isn't that easy to use? I've noticed that people miss the remainder theorem problems on a test a lot, and I think the reason is they forget what the remainder theorem says. All it says is that if you want to evaluate a function, perform the synthetic division with that number in the box, and the answer you're looking for is the remainder. That's all it says. So we know how to do synthetic division, so there's no reason why we shouldn't ever be able to use the remainder theorem. Let's try it one more time. And if you want to try this one on your own, feel free to pause the video. This would be a good time. And try this one on your own. But let's go through it together now. So it says, let f of x equal x to the third minus 4x squared plus 2x plus 1. Use the remainder theorem to find f of negative 1. Okay, well that tells me I need to do the synthetic division with negative 1 in the box, and the answer I'm looking for is the remainder. F of negative 1 is the remainder of this division. Okay, so I'm going to put down my coefficients, 1, negative 4, 2, and 1. And I'm going to put my negative 1 in the box. Of course, remember, I'm dividing by x plus 1, but that means negative 1 shows up in the box. Okay, pull down the 1. Now multiply, add, multiply, add, multiply, add. And I just found out that f of negative 1 is negative 6. All there is to it. Now that we understand the remainder theorem, let's take things a step further and talk about testing potential zeros. So what is a zero? A zero of a polynomial function is a number that you can plug into the function and get out a value of 0. On a graph, the real number zeros are the x-intercepts of the graph. Now, the remainder theorem gives a quick way to decide if a number k is a 0 or not. All you have to do is use the synthetic division to find f of k. If the remainder is 0, that means f of k equals 0, and that means k is a 0. If the remainder is not 0, then k is not a 0 of f of x. Another way to say that something is a 0 of f of x is to say that it's a root or a solution of f of x equals 0. These are all different terms for pretty much the same thing. Now let's take a look at example 3, which says decide whether the given number k is a 0 of f of x. And our function is x to the third minus 4x squared plus 9x minus 6, and the k they gave us is 1. So they want to know if 1 is a 0 of f of x. In other words, they want to know, can we plug 1 into our function and get a value of 0? 1 is a 0 of f of x if f of 1 equals 0. Well, one way to find that out would be just to plug the 1 in directly and evaluate it the way we learned in chapter 2. But we just learned the remainder theorem, so let's practice with that. If we do the synthetic division with 1 in the box, we'll know the value of f of 1 from the remainder. So here are the coefficients of my function. X to the third coefficient is 1, x squared coefficient is negative 4, and so on. And then I'm going to put 1 in the box. And now we'll go through the synthetic division process. Pull down the 1, multiply, add, multiply, add, multiply, add. Okay, the remainder is 0. That means f of 1 equals 0. And that means 1 is a 0 of our function. And that also means, in other words, 1 is a solution of the equation x to the third minus 4x squared plus 9x minus 6 equals 0. And another word for solution is root. And this is still example 3, but this is part B. So we've got f of x equals x to the fourth plus x squared minus 3x plus 1, and we want to find out if negative 1 is a 0. So we'll note that negative 1 is a 0 of our function if f of negative 1 equals 0. So let's do the synthetic division. This time, notice we go from x to the fourth to x to the second. Our x to the third term is missing, so when I copied down my coefficients, I left a 0 here. X to the fourth, x to the third. Here's my coefficient for x to the fourth, x to the third, x to the second, x, and the constant. And now, since I'm trying to evaluate f of -1, I'll put -1 in the box. And let's go through the process. Pull down, multiply, add, multiply, add, multiply, add, multiply, add. And now we know that f of -1 equals 6. So that tells me that -1 is not a 0 of this function. And here is part C of example 3. Here's a new function, and this time the k they are giving us is a complex number. Okay, 1 plus 2i is a 0 of our function if f of 1 plus 2i equals 0. Well, it might feel a little scary at first to do this process with complex numbers, but we can do it. We'll just have to be careful, and we'll have to remember that I squared equals -1. So let's copy down our coefficients. There'll be 1, -2, 4, 2, and -5. And notice I've spread them out a little more than usual because I'm going to be multiplying by a complex number, and it has 2 terms, and it's going to take up more room. So I'm going to put that 1 plus 2i in the box. And it's the same process, it's just when you multiply with complex numbers it can get a little more complicated. And let's see, we pull down. 1 plus 2i times 1 is 1 plus 2i. Let's put that here. And now let's add. Remember, when you add complex numbers, you go real part to real part and imaginary to imaginary. So -2 plus 1 is -1, and 0 plus 2i is 2i. Okay, now we're ready to multiply. 1 plus 2i times -1 plus 2i. This requires a FOIL operation. You might go on a corner of your paper or somewhere and just work this out. First times first is -1. Outer times outer will be 2i. Inner times inner will be -2i. And last times last will be 4i squared. Well, remember, I squared is -1. So 4i squared becomes 4 times -1, which is -4. And now let's combine like terms. Our real numbers are -1 and -4. Together they make -5. And our imaginary numbers cancel out. 2i minus 2i goes away. So we're left with just -5. I'll put -5 right here. Now add. 4 minus 5 is -1. Now multiply. 1 plus 2i times -1 is going to be -1 minus 2i. Now add. 2 minus 1 is 1. And then 0 minus 2i is minus 2i. Now multiply. 1 plus 2i times 1 minus 2i. I can't do that in my head. I'll have to do it on scratch paper. It's a FOIL process. First times first is 1. Outer and inner cancel out. And last times last is making -4i squared. -4i squared is the same as -4 times -1, which is +4. Now 1 plus 4 is 5, so I'm going to put the 5 here and add, and I get 0. So we just found out that f of 1 plus 2i equals 0, and that means 1 plus 2i is a 0 of our function. Now I've got 2 more here for you to practice on, one where they're asking us about a real number, and the second one where they're asking us about an imaginary number. So I want to encourage you to pause the video and work the next 2 out on your own, and then we'll go through them together. Okay, here we go. So to find out if 2 is a 0 of our function, we'll just need to do synthetic division on this with 2 in the box. So let's take our coefficients, which will be 1, -3, 4, and -4. And let's put the 2 in the box. And now let's pull down and go 2 times 1 is 2. Now add, now multiply, add, multiply, add. And we find out that the remainder here is 6. So that tells me that f of 2 is 6, and that tells me that 2 is not a 0 of this function. Okay, let's try to see if 2 plus I is a 0 of this function. Now this is just a little one, so this won't be too bad. We'll put our coefficients down, and then we'll put 2 plus I in the box, and now we'll pull down the 1, multiply 2 plus I times 1, you get 2 plus I, we'll put that here. Now add, 3 plus 2 is 5, and now multiply 2 plus I times 5 plus I. You can't do that in your head, so write it down. FOIL operation, 2 times 5 is 10, outer times outer is 2I, inner times inner is 5I, last times last is I squared, which is negative 1. Okay, now when you combine the like terms, you get 9 plus 7I. Put that here. Now add. You get 13 plus 7I. And so the answer is f of 2 plus I is 13 plus 7I. So 2 plus I is not of 0 of this function.